Okay, ladies and gentlemen, let's talk about perfect squares. Now, this may sound very different than our last section on sequence and series, but it's not really that different. In this case, how many blocks do we have? Well, we have one block. And that block is 1 unit by 1 unit. You could call it 1 inch by 1 inch or 1 foot by 1 foot, but it's one block. Now, in this case, if all of a sudden I take one block, but instead of just one block by one block, I make it 2 blocks wide and 2 blocks tall, how many blocks do I have overall? And here I come up with, instead of 1 block or 2 blocks, I have all 3 blocks wide, 3 blocks tall. That comes up with 9. Now, in this case, we're getting bigger and bigger and bigger. Let's see if we can find a pattern. Now, from here we have 1 to 4, 4 to 9. The next one is going to be 1, 2, 3, 4 tall, 1, 2, 3, 4 wide. If I count them all up, I come up with 16. All right? I come up with 16. So in this case, there's 3 different. In this case, there's 5 different. In this case, there's 7 different. Who can tell me what the next one's going to be? Five by 5, I come up with 25. Well, 3, 5, 7. What is 25 minus 16? That is 9. So we're obviously not adding the same amount. We're obviously not multiplying by the same amount. In this case, it was 1 times 1 is 1. 2 times 2 is 2. 3 times 3 is 9. 4 times 4 is 16, and 5 times 5 is 25. These are called perfect squares. Now you'll notice they're called perfect squares because as long as it's the same height as it is wide, they are still squares. And they're perfect because they're exactly even width to height. Now, what you need to be able to know is all of the first 10 perfect squares. So, this is written in expanded notation. Let's write it as exponential notation. Three times 3 is 3 squared, which is also why they're perfect squares. That's why we call this little number a squared. And so we have 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49. Now, you could already multiply these. You know all of this in your multiplication tables. But there are a few that we use so often that really having them memorized is the way to go. And having them at the ready. If you can get from 1 to 10, you can get from 1 to 100. And those are your perfect squares. Now, that's going from numbers and squaring to get the answer for the number of blocks. I want to go the opposite way. That's called square root. If I know there are 36 squares, if I have a piece that's chunked up into 36 squares, how could I tell how wide or how tall it is? Well, if I know that this side is the same as this side, then I know that I have some unknown side times some unknown side, because the area is length times width, and that is x squared equals 36. Well, if x squared equals 36, how do I undo a square? Well, if I think back over here, 36 was 6 squared. So we could say x must be 6. What we've done is we've actually taken the square root. The square root, or roots, like where the roots of a tree are below ground, it's where the tree comes from. The square roots are the roots of what makes that 36. Now, we use a special symbol for that. It looks like a divide sign, but it has a weird hook at the bottom. And if I do something to one side of an equation, I must do it to the other. A square root and a square are inverses of each other. In essence, they undo each other. They're exactly opposite. So if I square root a square, they destroy each other and disappear. In this case, the square root of 36 is 6. Now, as you go to algebra, you'll learn slightly different, but for now we're just going to go with positive 6. Now, let's do it without the benefit of a picture. X squared, in example 1, is 81. So what does x equal? Let's square root one side, square root the other. What times what makes 81? Well, what times, not so much what, because I could come up with 3 times 27. But what is even? The same number wide is the same number tall. That's going to be 9, because 9 times 9 is 81. So the square root of 9, or square root of 81, is 9. Now, while we're here, we can do things that aren't perfect square roots. And these, however, though, are just going to be an estimate. If I wanted to estimate the square root of 20, well, let's look at our list. I don't see a 20 anywhere on here, but I do see a 16 and I see a 25. Well, 16 is a 4 and 25 is a 5 squared, so square root of 20 must be somewhere in the middle. The best we can say is that maybe it's about 4.5, because it's about halfway between the two. Now, if I were to do another example, and I have the square root of 90, well, you'll notice I'm using a wiggly equal sign, because it's not equal to something, but it's almost equal to something. In this case, 90 is between 81 and 100, so maybe it's about 9.5. What if I wanted in example 3 to have the square root of 17? Now in this case it's between 16 and 25 again, but it's a lot closer to 16 than it is 25. So maybe my guess would be not so much close to 5, but close to 4. Maybe it's 4.1. That's estimating using square roots. We'll talk a little bit more when we get into it in class.